All right, so it's me again from yesterday, if you remember, and if you were at the Fireside chat, also me again. So let's get started. I'll talk a little bit about performance and debugging performance problems in the field. So like the slide said, I used to be a movie star, and then I switched careers to writing databases. And I'll talk about three things. First of all, the environment that the database runs in, the CPUs, the networking, the storage. And this is something that we try to tune very heavily automatically, but we sometimes get it wrong. So it might be that you will never need to interact with this yourself, but it may also be that we will get it wrong and you will need to do some digging in to understand what went wrong, and perhaps we will help you to do that, and then we can fix it to make sure that the next one down the line doesn't hit the same problem again on a similar setup. Also, we'll talk a little bit about tracing and about metrics. There were also talks previously that discussed this, so there may be some overlap. So the environment. So the most important part, or the most fragile part of the environment, is the networking. There are lots of different network cards, and they have different configurations. So we have to make sure that the networking is right. There's also the TCP/IP stack that can consume CPU power and perhaps do it asymmetrically and then could confuse Scylla. There's also the disk. We need to make sure that the interrupts are right, and talk a little bit about the write cache and problems with virtualization. So there are several different networking models that Scylla can use. The first one is the multiqueue. Modern network interface cards have multiple queues, and that means that when a packet arrives at the network card, it gets hashed, and then it is placed in one of the queues. And in the best case, you have the same number of queues that you have cores. So if you have 16 cores and 16 queues, then it's very easy. Each core gets one queue. The packet gets placed into a queue, and the core gets around to picking it up, and it processes it, and there is no core-to-core communication. This is similar to the way that Scylla works, where we try to have as little core-to-core communication as possible, and everything is fine. And the operating system is mostly bypassed in that respect. It's not bypassed in all respects. There is still TCP/IP processing that needs to take place. But in general, this is the best scenario. There is also another scenario, which is when you have just one queue. And in this scenario, we isolate a core for networking. And all of the packets arrive through that one queue into the core, which then divides the packets among the remaining cores. So in this model, Scylla will run on just those cores, and the networking will run on one core. And there is a two-step process where a packet gets pushed to a core, to the single networking core, and then it is analyzed and passed to the Scylla cores for the processing. And again, we try to detect this during installation time to figure out what the right networking model is for your networking card and for your CPU configuration. And there is also another networking model, which is a hybrid. And in this model, there is more than one queue, but not enough to feed all of the cores. And that was a little bit too complicated for me to draw, so I'll just describe it in words. And this is basically the same, the two previous pictures, but overlaying. There is a first step of distributing packets to some of the cores, and then these cores will take a further step and do this in software and distribute the packets to the rest of the cores. And that is used on really large machines where you don't have enough hardware queues. Hopefully, in the future, we will get more capable networking cards that have lots of queues, and then we can use the multi-queue model all of the time. So where is this configured? How do you know which model the system is running? So Scylla setup will detect it when you install the system for the first time, and it's stored in this file, perftune.yaml, and there is some information there about which CPUs are used for what part, what is the NIX that is being tuned, and the mode. Here it is using a multi-queue mode. So what happens when we get this wrong? So you can see this in this slide here. So you can see that you have the cores using some amount of CPU, approximately 1/3 of a CPU for user space processing, and you actually want that to be a lot higher. You want Scylla to use all of the CPU. And if you look at the idle time, you see that there is one core that is very, very busy, and the rest have a lot of idle time, and that is bad. You want the cores to be busy. So now you start to look why that particular core is so busy. So you scan it, and you see that it's doing more system time than the rest of the cores are doing. And in particular, the SI column, which stands for software interrupt, that is very high. And that is usually the case where you're doing a lot of TCP/IP processing. So in this case, the networking did not get distributed correctly to all of the cores, and there is just core 0 doing all of the work, and core 0 is strangled. And because the nature of a distributed system is, when you have a shared nothing model, is that the system runs at the speed of the slowest component, and all of the other cores are slowed down because of that. So that is how you recognize this situation, and you know that something is wrong. Usually to fix it, you need to dig deep into the configuration, but it's really a good idea to involve the development team at this stage, and we can help you with that and also make sure that the bug is fixed. It could happen because there's a networking card that doesn't correspond exactly to how it should, or maybe you have a weird networking configuration, but it's usually things that can be fixed relatively quickly, and then it's fixed for good. Okay, let's switch to the disk write cache. SSDs and regular disks as well have two different types of write caches. There's a write back cache, and there is a write through cache. So let's start by explaining what happens with a write back cache. We write something to the disk, and the disk, for its own reasons, doesn't write it immediately to the media. So it just places it into a DRAM cache and says, OK, I've completed the write, but it's actually lying. The data is in DRAM, and if you lose the power, then that data is gone. But everyone knows that, so it's not surprising. We just continue on writing, and we know that there may be some data that is on the disk cache. The disk will try in the background to write the data to the media, either a spinning disk or the flash cells, but there is no guarantee that it will arrive there in time. So there is an additional step, and that additional step is a flush, where we ask the disk to make sure that all of the data in the write cache has been committed to media, and we wait for that. Now, the problem with that is that the cache is usually pretty large, and therefore, if it gets heavily filled, waiting for the flush to complete can be a very lengthy operation. So you may encounter a stall in that area. So this is a diagram of what's going on. You can see that the write is acknowledged very quickly, and the media access starts, but it doesn't actually complete. So the data is acknowledged before we are sure that the data is on the media. So the important thing is the flush that waits for the media access to complete, but again, that can take a pretty long time. So there is also the write through cache, which actually should say here write through instead of write back. And it's really very similar. It's not just similar because I forgot to change write back to cache through. It's also similar because the things that are happening are very similar. There is one major difference. The difference is that even though we place the data in the DRAM cache as usual, it's not like we do the media access immediately as you would expect. It's still written into the DRAM cache. The difference is that there is an additional energy storage. Usually it's a capacitor or a battery. And that energy storage allows the disk to complete the media access even if you have a power failure. So it means that even though that the disk acknowledges the write before the acknowledge, we know that it will complete eventually. And so when we ask to flush, then the disk controller can acknowledge immediately, or even in some cases, the operating system can know that the cache is backed by a battery or by a capacitor, and so it doesn't even send the flush because it knows that the data is protected by the capacitor. All right, so what can you do about write back and write through? So if you have, most enterprise disks have a write-through cache, and you can see that with, by looking at the sysfs file. And if you have that, then you're good. And you should really check, when you're buying disks, you should check whether they have write-back or write-through cache. Ask the manufacturer, because that can make a significant impact on write-heavy workloads. If you, most consumer drives are write-back, so don't use consumer drives. Most enterprise drives are write-through, so use that, but not all of them, so be careful. Another thing that can happen with storage is iowait. What is iowait? It's in top, or there is a column that is called WA, which stands for iowait, and it means that the CPU is idle, but it's not idle because it has nothing to do. It's idle because it's waiting for the disk to complete work, but the disk is busy and is not responding in time. We've written Scylla with a lot of attention to that. So usually you will see iowait in the range of 0 to 0.1, 0.2% of the CPU. But if we get something wrong, if we got automatic tuning wrong, then you will see a lot of iowait. And basically, Scylla here is waiting for the disk to complete reads or complete writes, and is not able to do any processing in parallel. Usually, we try to parallelize disk access and compute, but here, because the kernel is waiting, then we don't get the CPU to do that. So this is something that you need to watch out for. It's pretty rare, but when it happens, it's a disaster. So what can you do when it happens? You have to contact us, and it's usually pretty involved, but we have some experience in dealing with it. All right, tracing. There are 3 types of tracing that are available. There's a single-shot tracing, where you just say, I want to trace this particular query. There is the probabilistic and the slow query logging. So what's the single-shot tracing used for? You're developing a query, and you want to understand what's going to happen when you run it. So you can just run it directly from a SQL shell. There is a tracing on command. And as soon as the query completes, you will get a trace explaining exactly what happened while that query was running through the system. And that's pretty useful to gain an understanding of how the system works. Probabilistic tracing, this is useful, and probably not to anyone here, because you probably all know exactly what's going on in your systems, but other people might not. They might have a complex application that they didn't develop all of it themselves. So you might want to know exactly which queries are running through the system and what is the relative distribution. So to do that, you use a probabilistic tracing, which means that a certain fraction of all queries will get traced. Those traces get dumped into a system table, which you can then query with a SQL shell. And it's really recommended to start with a very low probability. If you start with a high one, then what ends up is that the system is doing, all of the system throughput is dominated by writing the tracing output instead of actually doing your work. So use a really low number. If you don't get enough samples, then you can increase it later. But it's a lot better to start low and increase than start high and then panic. Slow query logging is for the long tail. So if most of your queries complete in time and you're happy, but you have some that take a really long time, then you can use the slow query logging. And you enable that via a no tool command. But the problem with that is that the results are not often, not always correct. So sometimes you might have a query that is perfectly fine, but during its execution, a lot of other queries interfere and cause it to slow down. And we don't really have a good solution for that at the moment, so you just have to watch out and try to understand exactly what's going on. It's not the best that it could be, but we're working to improve it. Metrics. So we just heard that metrics are important, and indeed they are. I'll talk a little bit about the different metrics that are available for Scylla. So first, you need to remember that metrics can be aggregated, and that sometimes hide a lot of information that's important. And you can also look at the metrics on a shard level, but then you might get too much information. There are CPU metrics, IO metrics. We talked a little bit about IO before. And in terms of the specific Scylla metrics, they can be roughly split into coordinator side, which happens when the query is accepted into the system and the system decides what to do with it, which nodes to send it to. And the replica-side metrics, which deal with the cache, with sending the data to, with fetching the data from the disk or writing it to the disk, and both are important. So the way to look at all of that wealth of the data is to start with a cluster level view and just look at what the cluster as a whole is doing, and then look at individual nodes and try to see if any one of them stands out. Things like the reactor load are very important. If one of the nodes is running at 100% load, then that node will usually dictate the speed of the entire cluster, because the cluster runs at the speed of the slowest node, and the same with shards. So once you identified which is the slowest node, you can zoom in again and look at the shard level and see which is the slowest shard. So CPU metrics, if you have a high throughput load, if many applications are really latency sensitive, but there are also some that deal with ingest, that need to ingest a lot of data, and you really want to push the cluster as fast as it goes, and you don't care very much about latency. So for those types of loads, you want to achieve 100% load. And if it doesn't, then you want to understand why. Very often, it's that you have one shard or a small number of shards that did reach 100%, and they're blocking everything else. So you want to understand exactly why that happened. It could be that you have a hot partition. It could be that you have a problem with the networking environment, like I mentioned in the beginning. You need to go and check those things. Another thing that can happen is that you don't have sufficient concurrency. So if you have a cluster that has 10 nodes, and those 10 nodes have 64 shards, then you have 640 CPUs that are all working. There is also network delays. So if you send them just 640 operations, most of the time we will wait for the next operation to complete. So for a high an ingest load, you will want a lot of concurrent operations to be running at once. So there is always enough. There is always an operation that can be run on one shard and have several more waiting for it on the network, so that we never have to wait for a network round trip. The IOQ metrics. So as you might remember, in Scylla we separate IO according to its type. There's IO that is used to serve queries, your reads. There is IO that is used to serve compaction, which is a background job that tries to reorganize the data. And the commit log, which is used to serve writes. So for each of them, you can monitor the bandwidth and the I/O per second. And if you divide them, you get the average size of the most important for queries. So you know the average amount of data that is accessed per query. And make sure that it matches your expectations so that you don't see reads that are a lot more than you expect. Perhaps the most important metric is the delay. So if there is not sufficient bandwidth available in the system, then Scylla will delay one or more of the queues. And it's important to figure out which one it is and see if it matches what you would want and how long the delay is. So if the delay is pretty long, then maybe your disk is not up to the task, or maybe something is misconfigured. You might want to get faster disk or get better disk, or spend some time investigating whether there is a misconfiguration. And it's a good idea to correlate it with the iostat command just to make sure that there isn't some glitch somewhere. It's always good to look at the same data from multiple points in order to be sure that there's not some component that missed something. Coordinator-side metrics. So again, the coordinator is a part of the system that accepts a query from the driver, from the client, and decides how it is to be handled. So the most important one is an amount of requests per second. You want to make sure that it matches your expectations. But if it doesn't, then we need to try to understand why. So first, we have to make sure there are enough connections to the database. Ideally, we want at least one connection per shard. So again, if you have 10 nodes and 64 shards each, you need at least 640 connections in total. And you want to make sure that they're distributed correctly. In Scylla, there is an automatic connection load balancer, so it will try to distribute the connections among all of the shards. But you want to check on that and make sure that it worked correctly. It's a good idea to check on the connection open rate so that we're not connecting and very often and creating new connections, because the overhead for creating a connection is pretty high. So perhaps your client is misconfigured and it continuously recreates connections. And if that happens, you want to fix that to get good throughput. Prepared statements, I think Shlomi covered that in his talk. You want to make sure that your connections are prepared, and you always, instead of building up query strings by concatenating strings, you just send the query string once to the prepare command and then reuse that query with bound variables. It's more secure, and it's way, way, way faster. It can be more than twice as fast in some cases. There are some metrics that are designated storage proxy metrics, and the important ones are the foreground reads and writes and the background reads and writes. The difference between foreground and background is whether we've already achieved the results that we want to send back to the client. So when the query starts, it's in the foreground. We start to collect responses from different replicas. We merge those responses, and then we send the response to the client, and then the query moves to the background stage. It might be empty for some queries, but for many queries, there is still some processing that goes on in the background. For example, a quorum write has to wait until we have 2 replicas acknowledge the write, and then it continues in the background until the 3rd replica, or perhaps more if you're using a large replication factor, responds. So you want to make sure that both the foreground reads and the background reads and write are not exploding. They are bounded. Exactly what number is right for your cluster depends on your nodes and on the types of queries that you do. So you need a little bit of intuition, which is achieved just by staring at the graphs for a long time. Reconciliation. Reconciliation happens when the data is mismatched. That can happen because a node was down. So you can look at the storage proxy metrics that measure the amount of time we had a read repair. And if those are high, then you know that perhaps you have networking problems, or you have some type of problem that causes that. It can really slow down your queries. So it's a good metric to watch for. All right, after the coordinator decides what to do with the query, it sends those requests to the replica. And there are some important metrics there. So first of all, there are the reads and the writes. So for each node, you will see the coordinator side reads and writes and the replica side reads and writes, but those are different reads and writes because the coordinator will dispatch your read to a different node. So if you see a high read count on the coordinator side, it means it has a lot of communication with the driver. If you see a high read count on the replica side, which might be on the same node, it means that there is a partition or perhaps a set of partitions that are seeing a lot of traffic, and that means that the distribution of the partitions is not good. Another thing is to look at the cache hits and misses, and if you divide them, it's the hit rate. And again, there is no right number. There are some loads where you would expect a very high hit rate, and there are some loads where you expect a very low hit rate. It really depends on the application, but it's important to match it with your expectation. You know the distribution of your data. You know how the temporal locality is, so you can check whether it matches with what you think it should be. The cache total memory, there is a metric that tells you how much memory is used for the cache. And usually it's not very interesting. Almost all of the memory should be used by the cache. That's the way Scylla was designed, to squeeze make use of every bit on the machine for cache. But if you see sudden drops, then that means there was a hiccup in terms of memory allocation. For a moment, Scylla needed to allocate a lot of memory. And to do that, it had to drop a lot of cache. And that's a problem that we want to know about. Again, there is not a lot that you can do about it. But if you communicate it to us, then we can usually identify what the problem was and fix it. If a query did not hit the cache, then it goes to the SS table. And again, we have two important metrics: active SS table reads and queued SS table reads. The active reads are the reads that are actually accessing the disk right now. If the number is high, then your disk load is going to high. If your disk is not very fast, then the latency is going to go up. And the metric after that, the queues SS table reads, is even worse. It means that Scylla sent as many reads to the disk as it was able to, and the rest it's kept back in check. We don't want to send them to disk because those queries consume a lot of memory, and we want to make sure that we don't run out of memory. So they are being queued, and they will only be admitted to the disk after the current query is complete. If you have queued SS table reads, it means that your I/O is exhausted, and you might either redesign your queries or get better disks. And lastly, current compactions. You want to make sure that those don't pile up. So in summary, there are a lot of moving parts, and even though we try to automate everything, something can go wrong. The application might get things wrong, and you really need a combination of methodical approach. You need to make sure that you don't miss some things just because you forgot to look at them, but you will also need intuition, and that means spending some time and looking at the system when it is performing correctly, so that you know the deviant behavior when you see it. And the most important is when you find something is wrong, tell us about it so that we can fix it, and it will not happen to you again or to your colleagues. Thanks a lot.